Hello everyone, thanks for having me. My name is Marshal Arijona. Today I will present my paper titled Least-Square Adversarial Autoencoder. This paper is authored by me and my colleague Mr. Lim Yohanes Stefanus. Both of us come from University of Indonesia. The outline of my presentation are as follows. First, I will talk about the introduction of our research. The second part, I will talk the method that we propose on our paper. The third, I will talk about the result and analysis of our experiments. And finally, I will talk about the conclusion of our research. So let's get started. Deep learning has made a tremendous result on supervised manner, especially on image classification. However, the progress of deep learning and representation learning still needs a lot of improvements. One of the most famous deep learning networks that can help to solve representation learning is Autoencoder. Autoencoder tries to reconstruct the data by utilizing the latent variable. The latent variable distribution can help to estimate the distribution of the data. Unfortunately, the continuity of the latent variable distribution cannot always be assured. This condition leads to the inability of the autoencoder to generate data that's similar to the training set. Another well-known representation learning method is generative adversarial network. This is a deep learning network that can generate new samples that's similar to the training sets by sampling a vector noise that came from the prior distribution. Generative adversarial network itself has so many variants, including info gain, Wasserstein gain, energy-based gain, and least square gain. Our paper tried to combine the autoencoder and the gain so we can assure the continuity of the latent variable distribution, and by set this condition, we hope that we can generate new samples that's similar to the training set. The problem statements of our research are as follows. First, how to combine least-square generative adversarial network and autoencoder into least-square adversarial autoencoder. Second, how to implement least-square adversarial autoencoder. Third, how is the quality of image reconstruction of least-square adversarial autoencoder. And the last is, how is the quality of image generation of least-square adversarial autoencoder. Now I will talk about least-square generative adversarial network, also known as LSGAN. Generally, GAN is a deep learning network that consists of two main networks called generator and discriminator. Generator tries to produce a data X called X-axon that is similar to the data X that came from the training set distribution. This can be done by a sample vector noise Z that came from the prior distribution and pass it to the generator network. The data that produced by the generator then will be passed into the discriminator network. Discriminator network tries to distinguish whether the data came from the generator or from the training set. We call this network as an adversarial network because both of the network works in an opposite manner. The discriminator will utilize the objective function to improve its skills to distinguish the origin of the data, while meanwhile the generator will use the objective function to improve its skills to produce the data that's more similar to the training set distribution. The difference between LSGAN and the original GAN is on its loss function. LSGAN uses least square loss function as its function on the discriminator and the generator. This cost function is often used on the linear regression method. Theoretically, least square generative adversarial network tries to minimize the Pearson divergence between the real data distribution and the generated data distribution. Okay, now let's talk about the autoencoder. The autoencoder is a deep learning network that consists of two main networks, the encoder and the decoder. The autoencoder works as follows. First, we have a data X. The data X will be passed into the encoder network. The encoder network tries to map the data X into a code or the latent variable Z xn by using the encoder function called g theta g. Theta g means the weights parameters of the encoder. So this is what we call as theta g. The second network is the decoder. Decoder tries to map the latent variable z xn into x xn using a decoder function called q theta q. Theta q means the weight parameters of the decoder, and this is what we called as the theta q. The autoencoder tries to reconstruct the data. It means that it tries to minimizing the difference between the x and the x axis. But the most important thing about the autoencoder is the z, or the latent variable. Autoencoder tries to find a simple representation of the data, so we can find a simpler distribution to estimate the distribution of the data X. Okay, now let's combine the autoencoder and the LSCAN. So least square adversarial autoencoder, or LSAA, is an autoencoder with an additional network called the discriminator. The discriminator tries to distinguish whether the data came from the prior distribution or whether it came from the latent variable distribution. LSAA works as follows. First, we have a data X, then the encoder will transform the data X into a latent variable Z xn. Latent variable then will be passed again into the discriminator that will produce the probability that the data came from the latent variable distribution. This network is also applied into a vector noise, so it will transform a vector noise Z and produce the probability that the data came from the prior distribution. The encoder is also works as the generator on this network, means that it will try to generate a latent variable that similar to the vector Z that came from the prior distribution. So it will also improve the probability that the discriminator will guess that the latent variable came from the prior distribution. The latent variable then will be passed again into a decoder network that will transform the latent variable Z xn into the X xn. So all of the network is parameterized by the data. What I mean by the data is the weights on each of the networks. LSAA have two main objective functions. First, minimizing the reconstruction error between the X and the X axis. The second one is to minimize the divergence between the prior distribution and the latent variable distribution. Specifically minimizing the Pearson divergence between these two distributions. Now I will explain the architecture of the LSAA that we use on this research. The architecture consists of 4 convolutional layers on the encoder networks and 3 convolutional layers on the decoder networks. For the discriminator networks, we use 5 fully connected layers. We choose fully connected layers since the latent variable only have 20 dimensions. For the prior distribution, we choose a Gaussian distribution with mean equals to 0 and standard deviation equals to 1. On this research, we evaluate two metrics. The first one is the reconstruction quality. We measure this aspect using mean square error, also known as MSE. The ideal score of MSE is 0, means that both of the data is identical. And the second aspect that we try to measure is the generation quality. We measure this aspect using threshold inception distance. The ideal score for this threshold inception distance is also 0, means that both of the data distribution is identical. We modeled the LSAA by develop a Python program. For the software tools, we use Jupyter Notebook and PyTorch as its frameworks. For the computing resource, we use DGX1 provided by Tokopedia UI AI Center. On our experiments, we use two dataset benchmark. The first one is MNIST, and the second one is our Fashion MNIST. MNIST is a grayscale image of digit numbers, and Fashion MNIST is a grayscale image of a set of fashions. Both of these datasets consist of 70,000 datasets, and we divided 60,000 for training and 10,000 for the testing. Here are the reconstruction results of our model. Our model achieved mean square error equals to 0.008 on MNIST dataset and 0.0099 on the Fashion MNIST dataset. We also compare our experiment results with the experiments conducted by Depelo and his colleague, whether they tried to test their models, variational autoencoder and Wasserstein autoencoder also on MNIST and Fashion MNIST dataset. The environment settings between our testing set is the same. We found that our model is better than the variational autoencoder, but slightly worse than the Wasserstein autoencoder. So here is the examples of the reconstruction of our model. From the picture, we can see that on some image, the reconstruction results lose some details. It's because the dimension of the latent variable that we use is relatively small. So the next one is the generation results. We found our model achieve FID equals to 11.128 on MNIST dataset and 27.5737 on Fashion MNIST dataset. We also compare our model with the experiments conducted by Lucic and his colleague, where they tried to find the FID scores of each of generative models. They try to measure the score on MNIST dataset and Fashion MNIST dataset. We also set our testing environment the same with the testing environment set by Lucic. We found that they found that the variational autoencoder gave the worst result on both of the data sets, and Wasserstein again gave the best result on both of the data sets. Based on the FID score, we conclude that our model is also able to generate new samples that are similar to the training sample. Here is the example of image generated by our model. We can see most of the images can easily recognize as one of a digit image, but there's some outliers here, as we can see on the Fashion MNIST, where we have a little difficulty to recognize the image. but most of the images on the fashion MNIST, from the generated fashion MNIST is easily recognized by our eyes. So this is the conclusion of my presentation. First, the contribution of this research is the investigation of least square adversarial autoencoder, an adversarial autoencoder that uses least square generative adversarial network plus function on its discriminator and generator. Second, in this research, a Python program was made to model the least square adversarial autoencoder. The program was implemented using PyTorch framework. The program was executed using Jupyter Notebook. The program utilized DGX1 computing resource provided by Tokopedia UEAI Center. The mean square error results show that the least square adversarial autoencoder has good reconstruction capability. Threshold inception distance results show that least square adversarial autoencoder is also able to generate images similar to the training samples.